And so it's gonna give you a very, very brief summary about the periodic table, atoms, and chemical elements. I'm going to keep it low key, and we definitely not cover everything. If you had a chemistry class before, you may go, well, this is really chemistry light. I'm going to try to focus on things and build you up to things that are kind of important for this class. And hopefully they will start making sense to you. And also, I don't know how much chemistry background you have since we waived the prerequisites. We're going to go through the whole 9 yards, so stick with me. Here we go. So prerequisite lecture series, I'm going to start with the periodic table, atoms and elements. So a little bit, what do we know about the atom, the makeup of an atom? Quick, so let's assume this is an atom. Blew it up, of course, a little bit. It's made out of several parts. It has an atomic shell, kind of something that's the outside of it, and it also has something in the inside we call the atomic nucleus. And they are composed of certain things. So the nucleus is made out of protons. These protons have a charge, and the charge is a positive one charge, and they also do have a mass. Now the mass is very, very small. It's calculated. We were able to figure this one out. We call it an atomic mass or atomic mass unit, an AMU. And it clocks in at 1.00727691 AMU. So a pretty precise number they have kind of put together. So it weighs something, even if it weighs little as a single proton in and of itself. If you take a whole bunch of them together in gazillions of atoms, it gives objects a certain mass. The other thing, so around this 1-to-1 AMU, we really don't need all this precise detail. One is good enough. The other thing that's also in a nucleus are so-called neutrons. Now, neutrons do not have a charge. Their charge is 0. But they do have a mass as well. So we were able to figure this one out. And they are roughly the same as a proton. So we're going to round this 1-to-1 as well. So both protons and neutrons do have masses. Proton has a charge, neutron does not, and they reside in the nucleus in the middle right there. All right. Now, what's on the shell? The shell is made up of particles. These are called electrons. And the electrons are smaller. They also have a charge. Their charge is -1. Kind of they balance out the charge of the proton. A proton is +1, so for each +1 charge of a proton, you must have a negative charge of an electron on that shell. And they do have a mass. We got this one figured out too, but this mass is really, really small. 0.00548580152. Whoa, very, very low. Actually, they're not even close to the mass of a proton or neutron. And here we're doing something really, really weird. We usually don't do this. We round that to 0. Their mass is really not having any effect on our atom. So we can round this 1 to 0. Let's take another look at protons, neutrons, and electrons. A little bit of a comparison. So 1 proton is equal to the mass of 1,836 electrons. That is somewhat of an interesting comparison. So in other words, if an electron weighed the same as a dime, a proton would weigh the same as a gallon of milk. And see how many dimes, 1,836 dimes, you would need to equal the weight of a gallon of milk. Also, as we have seen, a neutron is slightly, very so slightly, a tad heavier, but we're going to round it both to 1. That is good enough for what we want to do. Okay. Something else that's interesting, the nucleus and the shells are pretty far apart. To give you some idea, if we could shrink our sun to the size of the radius of 1 foot, think about the size of the sun as a large beach ball, right? And then we put the solar system to the same scale. our Earth would be then 215 feet away from this beach ball, and our outermost planet far out, we would need to travel on that beach ball scale 1.6 miles to meet Pluto. Now, if we blew up a nucleus of an atom, in this case a gold atom, to the same size of a beach ball, what would be our model equivalent to the electrons that kind of floating around this gold atom? What would be the most outside shell that, how far away from the nucleus would it be? And believe it or not, it would be twice as far, 3.3 miles. So in atoms, we have an incredible amount of empty space that is not occupied. It's really empty space. It's nothing there. And that has given rise to certain sci-fi movies. One great flick that came out, humorous, while was Honey, I Shrunk the Kids. And in this idea was that if we could change that distance and basically shrink the distance down, then everything would become smaller, you or an object. The one thing I always find hilarious in those movies, may it be Avengers or may it be Honey, I Shrunk the Kid, you can shrink the distance, theoretically. Nobody has ever done it, we don't know how, and make things smaller. You wouldn't change the mass. So if you shrank your car to the size of a little matchbox car, like 2 inches long, it would still weigh the same as a car. So nobody could pick it up and steal it and carry it around, as these sci-fi movies make us believe. So the mass would not change. I still would have the same mass. But this is the idea behind it. I'll give you some, some model that you can picture in your head as we move on. So periodic table is a list of the elements we have discovered and isolated, and it has some symbols on it, and I will go really briefly through it to explain it for those who have had no background in chemistry yet. So one in the middle here, there is a letter symbol. That is the chemical symbol of the element. In this case, it's carbon, and it has the symbol C. You need to observe the nomenclature a little bit. The first letter of the chemical symbol is a capital. The second letter is lowercase, and there is a reason for this, because capital C with a lowercase o or capital C with a capital O are two totally different things. CO is indeed an element we call cobalt. It's a metal. And the other CO with both capitals is actually a gas. It's a compound we call carbon monoxide. So watch these nomenclatures when you type things up. That do you mean a compound or an element as you put those together? Then not all periodic tables have that. Some assume we are familiar. That is, of course, the given chemical name of my element, written often below. One number, usually on top somewhere and printed in bold, is what we call the atomic number. And the atomic number is kind of a very, very important counter, because it always counts the number of protons present in one single atom of this element. Now, what is important about this one is that protons define which element it is. So if you have 6 protons in the nucleus, that is always going to be a carbon. There's no way around that. It's always going to be a carbon atom. If you would change the number of protons, you would literally change elements. If it would change the number of protons on lead, for example, we could turn lead into gold. The problem is we don't know how to do that. It's inherent to each element. These protons are stuck like glue in the middle, and it's very, very difficult to mess with them and make my elements into something else. It is also the number that usually counts all the electrons that reside on the shells, on these shells of the atom. Remember, protons have a positive charge, electrons have a negative charge, and they need to balance each other out to make this whole thing neutral. So this is what the atomic number means. It's a little counter there. Down there's another number. Sometimes it's printed smaller, sometimes with a lot of decimals. That is the calculated atomic mass number. And the atomic mass number, of course, is the composition of all the protons and all the neutrons within the nucleus. Now, we already have the counter for the protons here as a 6. Well, we could calculate now how many neutrons must be in a carbon atom to give me an atomic mass of 12. That shouldn't be too difficult. So the atomic mass is the counter of number of protons plus the number of neutrons present. All right, so that's how we read these symbols. A little bit about reading the periodic table, basic element information. I just pick one. Here's my element with the atomic number of 20. That's the element calcium. It plays somewhat an important role in the geosciences. We'll see that later. So we can ask a question: how many electrons are usually present in calcium in its neutral state? We can think about it. We'll have some little assignments for you that you can try to practice yourself. But if you said that's 20 because that's the atomic number, you are absolutely right. We can ask the same question: how many protons are in calcium? And it should, of course, be the same number. We have 20 protons present in calcium. Let's give you this idea. How many neutrons, however, are in calcium? And to answer that question, we need to do a little bit of math. And here are the steps that you need to know. First of all, take your atomic mass that's printed and round it. In this case, we round it to 40. Then from that rounded number, subtract your atomic number, which is at 20. And so in calcium, we have 20 neutrons. Right? 40 minus 20 is 20. Now, you may ask, are there always the same number of neutrons as protons in an element? Often, but not always. There are some elements that are kind of off the beaten path. So keep this in mind. Many it matches. In this case, calcium matches. By the way, carbon matches too, but not all of them have the same number. So there are 20 neutrons in my calcium. Okay, let's try this again. I'll give you a few seconds to answer this one. How many neutrons are in strontium? Let's give you a minute to kind of do the math, see what you come up with a little scratch paper. You should be able to figure this out. If you want to, you can text me the answer. See how good you do. No points, just practice. Okay, let's give you the solution for this problem. So we're going to take the atomic mass again, and we're going to round it, in this case 88. And from that, we subtract the atomic number, which is a 38. And here you can see, strontium has a different number of neutrons in it. Actually, only more than protons. There are 50 neutrons in a strontium atom. Okay, that should be straightforward. A little bit about element names. There are some really interesting naming of elements. You may ask you, why is gold AU and not GO or something? Right? So first of all, it has to do with ancient history and ancient alchemy. A lot of these elements that were known to the antiquity or throughout the antiquity, like gold, borrow their names and their equivalent from planetary science and alchemy at this time, and it's usually their Latin names. So gold, the Latin name is aurum, and it got the symbol AU, and it stuck with it since colleges and universities in medieval time always had Latin as the science language. So a lot of things were published in Latin, written in Latin, lectures were held in Latin, and therefore these names stuck. So gold gets the AU from aurum. Mercury is kind of an interesting. Hydrargyrum, or can't even pronounce it, gets the Hg symbol. Copper, the Cu symbol from cuprum. Silver is argentum, gets the Ag symbol. Iron is interesting. This is why we refer to iron as Fe. Tin is sternum, gets the Sn. And lead, from the Latin name plumbum, gets the Pb symbol. And now plumbum is kind of interesting. This is how we take some of the terms in the English language. Think about this one. A person that was making pipes in the antiquity, creating pipes out of rolled sheet of lead, was called a plumber, because lead pipes were usually made out of lead. You've heard about lead pipes in old houses. Yep, there you go. So a plumber and plumbing are taken from actually that Latin root name right there. They were working with lead. Okay. Some other names here is tungsten. That doesn't make any sense. The name is tungsten. The symbol is a W. Tungsten was discovered way later. It's not an element of antiquity. That was isolated in a more modern chemical approaches around the turn of the century, and it got named in two different places at the same time. Some confusion. So tungsten is actually Swedish because it was extracted from some very, very heavy mineral ore. Tungsten is the Swedish word meaning heavy stone. That's where it came out of. The W actually was something that's a Germanic name given by German scientists of Wolfram. Translation is wolf's cream, because in the isolation process, you were making kind of a foamy, whitish substance, gray whitish substance that reminded the scientists of a pelt of a wolf, and they kind of called it wolf's cream. And so as things were published of this newly discovered element, I'm going to throw those two things together. So W becomes tungsten in the English language. I have a few more for you, just because they're kind of hilarious. Why is potassium K? Because potassium is already a Latin name. That has to do a little bit with the isolation process. A lot of these elements are locked together in compounds. They had to be isolated first. And the Latin word for alkali, this is where that one came from, is kalium. And so the K became the symbol. Actually, if you go to other languages, they call it kalium as well, and potassium from potash, the potash isolation process that we did later. So this is where some of these names come from that don't seem to mesh with the symbol as we put these element names together. So now we're going to have a little practice exercise for you. Have a periodic table ready and play with it a little bit. I'll see if you can do this. But how many protons in sodium? So go find your sodium on the periodic table, and then kind of on the screen, a piece of paper, may give you a best pick from these answer choices. What defines protons in an element? Remember that? Of course, that is the atomic number. So sodium has the atomic number of 11, and therefore that's the number of protons. I'll give you another question, see if we can find that in your periodic table really quickly. What is the mass of silver? Of course, now you need a periodic table that gives the atomic mass units. When I've scanned this one, you need to find silver first, somewhere on this list of over 100 elements. And then if you find silver, you should have something like 107.9, or it's a very similar number. Often they have some rounding errors as they do this one. I should see in a silver. By the way, if you cannot find silver, it's Ag. And it would show up. Okay, let's give you another question. Chemical symbol for platinum. Yes, it is one of the P's. And if you picked or it landed on PT, you're absolutely right. That's the platinum chemical symbol. I think I have another one for you. Fe, which element is this? We talked about it. It shouldn't be too hard. Give me a name for Fe. Ferrarium. I like that one. Of course not. It's iron. That was a stupid question, really. How many electrons are usually around surrounding the chlorine nucleus? Okay, I need to find chlorine and give me the answer here. Shouldn't be too hard. Remember, what does the atomic number tell us? And if you picked 17, you're absolutely right. That is the electrons that are usually the same as the protons in an element. If you picked, let's see, Al, absolutely right. I don't know if I have another question of those. Let me give it a shot. Yeah, which element is Ba? I need to find Ba somewhere on the list. There we go. Barium on your periodic table. So just this little, very simple exercise of how to read a periodic table. I bet many of you are already familiar with this. It was just a little review of data we can extract. Oh, there's something else. Neutrons and lithium. Let's try to figure this one out. I'll give you a few seconds here. Okay, remember how to do this? Atomic mass, round it. Atomic number, take the difference, and you should come up with a 4. All right, good. So let's go a little bit further into the periodic table of elements. A periodic table consists of 2 parts, rows, sorted by rows and sorted by columns. And the rows we actually call periods, hence the periodic table. The columns make up groups. So we have periods and groups. Actually, the full name should be the periodic and group table of elements. And they're sorted in a certain way. And so let's kind of go through the sorting process, see what we can talk about. So what do these periods and groups tell us? Is there any other additional information we can extract out of these 2 systems? All right, so electrons, where are they located? Well, we said roughly in shell. Actually, it's not one shell, it's shells. There's more than one electron shell, and these electrons are kind of distributed across there. So there is an electron configuration specific to each element. These electrons are not haphazardly all in one shell. They are distributed in a orderly fashion among these electron shells. You may also have heard about electron orbitals. Some of you have had chemistry that talked about orbitals. Now, we're going to do chemistry here that takes you a whole semester. We're going to do this in a few minutes. I'm going to rush through everything you need to know and really focus on the more specific things, the practical things of what to do about it. So here's an configuration. Let's try this one. So these electrons, as I said, occupy certain energy levels on the electron shell. And there are, if you want to make the analog, there are major electron shells and there are subshells that are attached to each major electron shells. So right now we're going to look at the major electron shells. Think about it, you know, how many apartments are in a housing complex? Those are my major electron shells. And then how many apartments are on each level? That would be the minor electron shells. So we're going to focus on the major ones, the big ones all around. Let's see if we can figure this one out real quick. So electron, and we call it also electron energy levels. Let's do this. Let's use a periodic table. How many periods do we have? If you take a periodic table and count all the periods, and here is a periodic table for you. And we're gonna count periods, and here's what you see. 1, 2, 3, 4, 5, 6, 7. There are 7 periods. Actually, these things down there, in case you ever wonder, they are otherwise the periodic table would be way long and would go over 2 or 3 screens on my computer. They often cut these ones out. They fit right in here. And this would stretch out the periodic table on a very long fashion, so they can put it on a sideways printed landscape page. They often take those out and print them down there. I'll give you some idea, but both of those periods kind of fit right down there. So if we do this, there are really only 7 major electron shells around each one of these atoms, and they can be occupied by electrons. Hopefully this makes sense. Okay, so how many electrons in each shell are possible? Can we do as many as we want, or are there limits? And yes, there are limits. There are only so many who occupy this. So what we're going to do is we're going to draw a model of a hydrogen atom. If you want to follow along, I'll give you here an example. It's just a nucleus, and in this case, I over-exaggerated the electrons so we can see it because we're talking about electrons here. So we kind of ignore the nucleus, we make it tiny and kind of stick it in the middle, and there it is. And we blew up the electron a little bit, and you can see there's my electron shell right there in hydrogen, and there's one lonely electron on there, and that should make total sense because, hey, hydrogen atomic number is 1, and therefore should have one proton at least and 1 electron out there. Let's go to the other edge of the periodic table. We're going to do the same with the helium. That was in our first electron level, drawing. They're all in the first period, and I'm drawing a helium there. And the helium, you can see, I have my nucleus. I make it small again. Here's my electron shell, and I have 2 electrons kind of mucking around on that one. That was period 1. What about the next period? If we add another period, how many major electron shells does that have? Second period down should have 2 major electron shells, and see how the electrons distribute. So let's try another one. Go to number 2, period number 2. Start with the lithium right there and draw that one. And what we see is, now we're going to get another electron shell there. Lithium has 3 electrons. The first 2 go in the first shell, and then the leftover goes in the next shell. You can see that. So 2 major electron shells, and it has 2 and 1 out there. It's in the second period. All right, I want to add to this one. Let's draw beryllium. We draw beryllium as an atomic number of 4, and you can see what happens. In the first shell, there are 2. And in the next shell, there are now also 2. So it gives us a total of 4. Now let's wander through this period to the right side a little bit. I'm not going to draw each and every one of them, but we're moseying along to the right side. We're going to get closer to the edge, to the end of the periodic table. And there's a fluorine atom. What would that look like? Again, it's in the second period, so it has 2 major electron shells. How many electrons do we need to draw for each one of those? Again, 2 shells, has 2 electrons in the first shell. That looks like is the limit. Can't fit any more on it. And everything else now goes in the second shell. What do we have here? 1, 2, 3, 4, 5, 6, 7. So 7 in the next shell. And the last element in that period is the gas neon gas. let's draw that one. And what happens here, I got 2, and then I get 8 around it, gives me a total number of atomic number of 10 for neon. So that was period 2. Let's try another period. It was so much fun. Let's draw sodium. That's sort of in my third period. Again, how does the distribution look like? Sodium is in the third period, has 3 major electron energy levels. 2 in the first one, 8 in the next one, and then the 1 extra one goes in a third level in this park there. Now again, I don't draw all of them here. You can fill it up, with each element, one group over, we add one of these electrons. And we're going to go all the way to the end, I think. Let me draw argon, the last one in that particular period. And if I drew this one correctly, then I have 2 in the first shell, 8 in the next one, and 8 in the next one. That is what we call electron configuration. Now, I realize I simplify this a lot. I focus on stuff that we may need to have for us being important. But here's somewhat the maximum occupation for each electron shell. So we got 2 for the first level. We got 8 for the second period or second level. And we got another 8 for the third level. And you can kind of figure out what might happen next. So 8 seems to be a magic number in the world of atoms as filling up these electron shells. And now we would need to go to the fourth period and add another electron shell and start occupying that one. So I'll let you test your knowledge. Now you know a little bit about how to draw things on a scratch paper. I'll give you a minute or so. And then we compare my beautiful drawing with your beautiful drawing and see what you get. So draw a nitrogen. Put all the correct number of protons and neutrons in the places where they go. Draw all the electron shells that would be present and how many electrons would be hovering in each one of those shells. Okay, here we go. So here's my little nucleus bouncing in. Looks like I have 1, 2, 3, 4, 5, 6, 7 of these protons hovering around there. My neutrons, I got 2 electron shells. It's in the second period. And I know there are 2 electrons in the first shell, and all the other ones that are left, 1, 2, 3, 4, 5, go then in the remainder of the shell. And there is my complete model of a nitrogen atom. Now, do atoms really look like this? Do they have like orbitals like we have orbits of planets racing around the sun? And not quite, but it's easy to draw. That's why we're using it. Actually, atoms look much more weird than this. It's more a cloud, and these electrons can be anywhere on this cloud area at any given second. So they just bounce randomly around there at a certain distance. Okay, but we're sticking with that. It's called the Bohr model if anybody is interested in drawing things this way. Now, number of electrons and the importance of how many of them are in the last occupied electron shell. Give you some ideas. So the importance of the last occupied electron shell, now we're going to get into a little bit of practical stuff, things we can use in this class a little later on. Here we go. If there's any action, like an explosion or reaction between atoms, the interaction is always on the last occupied electron shell. That's where the action happens. And so we need to understand how many electrons are on there and what they are doing, right? So what we're going to do next is, I'm going to show you, let's see, it's really interactive today. So you're supposed to work in sketch things out a little bit. So for each one of these questions, or the things I will show you, answer these two questions for each one of the following elements. How many electron shells are around the nucleus? The big ones, they're actually occupied. They have some kind of an electron floating around on there. That's your first question to answer. And then how many electrons are in the outermost, the last shell of these occupied shells? All right, ready? Here we go. Little exercise. Here I have them all. Okay, I'm back. Let's go back to our solutions there and see what I have drawn, and you can compare it with your pictures. So for my lithium, I have 2 electron shells around the nucleus, and I have 1 electron on the outermost, the last shell right there. My carbon, I got 2 electron shells again, and I got 4 electrons on the outermost shell sitting around there. Oxygen, 2 major electron levels or electron shells, and I got 6 electrons on the last shell right there. I'm going to frame them in red so you can see it. If you do magnesium, magnesium is in period 3, of course, going to have 3 electron levels, and I have 2 in the outermost shell, with the rest of them distributed in level 1 and 2. Aluminum has 3 in the outermost shell of its 3 levels. My chlorine, that was kind of a bear to draw if you want to draw the whole thing, has actually 7 electrons in its outermost shell. And we're going to do one more. Potassium. Potassium is in period number 4, so you need to draw 4 electron levels. Occupation is 2, 8, and 8 of the other electrons, and there's 1 electron left, and it has to go on the 4th electron level, and that would be kind of how many electrons are on the last occupied electron level. Why is that important? Because we're going to do something with it and help you figure out reactions and reactants as we move along. So now I need to tell you a funny story. My little fairy tale for today, the kingdom of elements. So once there was a king and a queen, and they lived in a kingdom. Actually, there were several kings and queens, 7 to be exact. And those kings and queens have an analog. I mean, they had certain names, and here comes the names. They were called helium, neon, argon, krypton, and xenon. There were a few more, but we'll stick with those 5 for general purposes. So this was the kings and queens in this kingdom. And these kings and queens had a lot of serfs, subordinates that were part of their kingdom that they could rule and reign over. And and all these serfs wanted to look like helium, neon, argon, krypton, and or xenon. And what did helium, neon, argon, krypton, or xenon look like? Well, here's a helium. 1 occupied shell was 2 electrons. Neon had 2 shells was 2 and 8. Argon had 3 shells was 2, 8, 8. And krypton had 4 shells was 2, 8. It's getting nuts here because we actually need to occupy a few more as we go out. And there comes xenon at the end. But always there seems to be 8 in the last occupied electron level. That's where they go. So this is what they looked like. Now, there are 2 of the serfs I want to introduce you to. We're going to use an example, sodium. Sodium was out there. And chlorine was out there. And both sodium and chlorine were totally infatuated with their kings and queens. If they would be teenagers, you would look in their rooms, they would have posters of their heroes, the neon poster, the argon, the krypton poster, looking like this, hanging on their walls because they wanted so much to look like them. They wanted to look exactly like them. Now here's the problem. The protons are fixed. You cannot become something else. Chlorine cannot become actually argon. Doesn't work, but it could look like it, right? To emulate what argon would do, say, and act. And so those two were kind of bummed one day. They so wanted to look like their counterparts here, like their royalties. And as sodium and chlorine were talking, sodium says, you look, if I could have 7 more electrons in my outermost shell, I would look exactly like argon. I'm not argon, but I would look like it from the electrons in there. And chlorine was thinking about, yeah, if I would just get 1 electron out there, I would also look like argon. And at first sodium was saying, well, chlorine, can I borrow 7 electrons for a while? And chlorine says, no, I already have that many. I just need 1 more. Why would I do this? And as they kind of contemplated back and forth, they came up with a brilliant idea. They say, sodium said, look, I have only 1. If I gave the 1 to you, you would look like argon. I lose 1, and then whatever is left, I'm looking like neon. Wow, let's make this exchange. And this is exactly what they did. So sodium gave freely 1 electron to chlorine. Now, if you look at this, now sodium looks like neon, chlorine looks like argon, and they have never been happier in their lives. They kind of looked like their elements. So we look like neon here, and it looks like argon on this side. But something happened to them in the process when they did that. Let's take a look. How many positive charges of protons does sodium actually have? Now, the protons are fixed. We didn't muck with the protons at all. That's why sodium is sodium. And if we count them, we come up, of course, with 11. So we have 11 positive charges inside a sodium nucleus. But how many electrons or negative charges does sodium now have after giving up 1? And if we can count those, sodium is missing 1, so it has only 10 negative charges. And you can see the nucleic charges do no longer balance with the electron charges on the shells. And therefore, what's happening? Well, what's happening is that sodium has an overage of a positive charge, and it actually becomes no longer a neutral atom. It is positively charged with a positive charge of +1. Let's do the same little investigation for chlorine, shall we? What about charges in chlorine? If we did the same thing, the nucleus is fixed. It has 17 protons in there. We cannot muck with those that are positive, but it gained 1 more electron. So it has actually 18 negative charges now instead of 17. Therefore, it has an overage of a 1 negative charge. Actually, chlorine becomes negatively charged by a factor of 1, and sodium becomes positively charged by a factor of 1. What does that mean? Well, you know that little chart. Like charges repel, but opposites attract. +1, -1, and chlorine and sodium flew toward each other, got stuck together, and lived happily ever after. They made actually a compound by trying to become like their royal counterparts. Welcome to the world of ions. Ions are charged elements that have either gained or lost electrons, have a charge imbalance. They become literally charged, and they will find opposites they can attract to and combine with, right? So anions are ions that carry a negative electrical charge, and they get their charge by gaining 1 or more electrons. Cations, on the other hand, are positive electrical charged ions, and they have that positive charge by losing 1 or more negatively charged electrons. I think it's time for a really stupid Dr. K joke. No. A proton what was it? Nah, better not. Yeah, here it goes. A sodium and a neon coming out of a bar, and the sodium says to neon, oh boy, I think I lost an electron. Neon says, are you sure? And sodium says, yes, I'm positive. Ha ha ha, stupid joke. Here we go. All right, so there's your cation right there, losing an electron. And of course, if you have a cation and an anion, they will try to stick together. So they combine to actually make compounds. However, you need to balance the charges. So a negative one must be balanced out with a positive one. And you need to make sure these charges are balanced. More about this later. So another stupid joke. Yeah, opposites attract. So my cations and the anions will like to stick together. Now, to help us a little bit with the visual of this whole thing, we can figure out these charges that the ions make by using something called the Lewis dot method. To give you some idea, what you need to answer is, and to draw a symbol with the Lewis dot method is, how many electrons are in the outermost occupied shell? That's the most important question. So how many electrons do I have there in the outermost shell? And the next question, also important, how many electrons can be maximum in that outermost shell? How many electrons can that one hold? By answering those two questions, you should be able to figure out what's going on. One more question to answer is, would it be easier for a particular element to lose or to gain these electrons? Remember, in the case of sodium, it was only one electron out there. It was much easier to give up one than, gaining 7 or something crazy. And for chlorine, it was much, much easier to just get one than getting rid of for 70. So what's easiest for this particular element? And we're going to draw this as little dots. So let's see if we figure this one out. Here's my little screen. Let's use neon. And basically what we're going to draw is the electrons in the outermost shell. And what would it be for neon? And I would draw 8 little dots around neon. To make it simple, I put, it in pairs of 2s, 2 on the right, 2 on the left, 2 on top, 2 on the bottom. I'm going to see these are the electrons in the outermost shell. All right. Neon, would it gain or lose any electrons? Good question. Neither. It has already 8. Why would it give up any? It is already happy as a lark. So it's all full. What would the charge be of a neon? Since it has no overages, it has a charge of 0. So there's no charge, no ionic charge for that one. Okay, let's try another one. What about magnesium? How would you draw magnesium? Again, what you need to do is you need to look at the periodic table. How many electrons do I have? How many electron shells I have? Distribute the electrons of the last occupied shell. And for magnesium, we'll come up with only 2. The easiest way to draw those, and we'll see why in a second, instead of drawing, 1, 2 on one side, start it like a clock. Start the first electron here, and the next one here, and so forth. Go around, and if there's more, then go around again and fill up these little extra ones. But magnesium has 2. Here comes the question: will magnesium like to gain or lose electrons? And as you probably note, it's much easier to give up 2 than to gain 6 more. So it likes to lose, much easier than gain 6 more. If it lost those 2, what would be its charge? Okay, 2 negative charges are leaving. Then my charge that is left would be an overage of 2 positives, would become +2. So magnesium ion has a charge of +2, and it would be a cation. Okay, what about fluorine? Again, look up fluorine in the periodic table. We are interested in how many electrons are in the outermost shell. We can draw this again with the little dots. Here we go. Almost there. Needs only one more. So for fluorine, you can ask the same questions really quick. Gain or lose? Of course, gaining here would be much easier than losing anything, right? What would be its charge if it gained that one that it's missing? Well, we would have an overage of a negative charge, and so all the fluorine ion would become a -1, as you can see. Well, this is so much fun. Let's try aluminum. How many electrons are in its outermost shell? Again, look it up in the periodic table. How many shells do you have? How many atoms, how many electrons reside in each one of the shell? And we are only interested in how many are in the outermost shell. And for aluminum, would be 3 right there. Or we can draw around aluminum. I think and then of course it would be much easier to lose those 3, so aluminum would have a +3 charge if that happens, if it lost those 3. Okay, what about sodium? We already had this one. You should have only 1, much easier to lose. So I'm getting a +1 charge if it lost that 1 electron. I'll try 4 more. I have calcium, chlorine, nitrogen, and oxygen. All right, I'm back. Are we ready for the solution? Calcium, again, electrons in the outermost shell, has 2. If it lost those 2, it would become a cation with a +2 charge. Chlorine, we already know that one, much easier to gain 1, so it would become a negative charge. Nitrogen, actually, if we just use the periodic table, has 5 out there. Probably easier to gain 3 than to lose 5, so it becomes a -3 charge. And oxygen has 2 vacancies there, probably easier to gain 2 than to lose its other 6. So that's a solution. Why are we doing this? Oh, one more. What about silicon? I'll let you draw that one. If you draw silicon and its last occupied level, you got 4 dots. Now here comes the question, what are we going to do with silicon? Does it lose 4 or gain 4? It's a good question. It's as easy as gaining 4 as it is to lose 4. So silicon is one of those. It can do either. And it can have a +4 charge. It also can be -4 charge depending on circumstances. So silicon is kind of a double whammy. It's right in the middle of that, of the system. Okay, good. Now, that charge, this ionic charge, we often refer to as valence. This is my ionic charge of elements. Can you do it? Again, I let you figure this one out. Here's my first question. You should be able to crank this out in a very, very short order. What's the valence of lithium? Use your periodic table. Again, how do you do this? Electrons in the last electron shell, gaining or losing, and you should get the correct answer. So for lithium, the answer would be, was a +1. Easier to lose just 1 electron than to gain like 8 more. What about sulfur? Okay, find sulfur. What we need is all the dots in the outermost shell and then figure out would it gain or lose something. And here we go. For it, it's easiest to gain 2. So -2 would be its valence. Valence of oxygen. And you take a look at oxygen, see if you can't figure this one out. We've drawn it before. Probably easier to gain 2 than to lose 6. So also -2 charge. Bromine. Okay, bromine, another one of those much easier to gain one than to lose 7 others. So the charge is a -1. Calcium we just did. You should remember this one. That was a +2. Argon. Let's try argon for good measures. See if we can't figure this one out. And that one is interesting. It's kind of a little trick question. Not really a trick question. As you notice, argon's energy level is full. It has no interest of gaining or losing anything more. It's already there. So it will not make an ion. It doesn't. This is why these noble elements or noble gases, they don't react with anything because their valence is literally 0, not doing anything.